Back once again. Today is June 25. This is day 12 or 13. I'm confused, but I've rested. My brain feels sort of all right. If I had to give it a scale of 1 to 10, I would say I'm at a 3. Yesterday I was at a 1. After some rest, I think I'm at a 3. Maybe a couple more nights, maybe I get to 10. But I read something, or someone told me, or a friend told me, I think that like if you don't sleep, or if you sleep for 7 hours every night for a week, after a week it feels like you didn't sleep for 24 hours. And I would say I still kind of feel like that. So we shall see. As in terms of what we're doing today, I think there needs to be a mix of new problems and old problems. So I won't say that I'm gonna raise the minimum. The minimum right now is always 20 minutes. Got to keep the bar low so it's easy to meet. I know that I can meet 20 minutes a day. Rain, sleet, or snow, uphill and downhill both ways. If I'm not feeling well or if my legs are broken, I think I can do 20 minutes. 40 minutes though, that is a risk. Maybe I'll have, maybe as I'm coming home from work, as I'm putting the key into the door, maybe I'll drop the key, and that might be the last straw I might snap. And in those days, I don't know if I can guarantee 40 minutes. So 20 minutes is the minimum. Even when I drop the keys, I know I can do 20 minutes. That being said, though, I think I'm going to maybe choose a branching system. I'm going to keep the bar at 20, but prioritize 20 minutes of old problems first, just because it's more important, I think, to do maintenance than it is to do newer problems. If I never, I think a good example is if you had a bucket, right? Leaky bucket represents your knowledge or whatever. If you keep pouring more water into the bucket, which is like getting more knowledge, but the bucket is leaking half of its content every 2 hours, then you're kind of playing like a game where you're only holding on to the least recent stuff you learn, and the older stuff you learn is just going out the bottom of the bucket, right? Because it's a leaky bucket. So I think maintenance is most important. Keeping the water that I already have in the bucket from leaking, I think, is more important than adding more water into the bucket. So I'm going to put an emphasis on older problems. After the 20 minutes of older problems, though, I should do a little bit of new problems, just because new problems help me not be so rigid. You need new scenarios, new sequences, probably just in life in general, maybe, so you don't stay so rigid. And I think the new problems help me with that. So if I learn how to do a problem, I don't want to keep the skills that I've learned siloed into a bubble in my brain called, two-sum or something like that. Ideally, what I learned should be kind of zoomed out and extracted into more general bubbles, so that every new problem I add adds more to the brain juice. So I'm going to do some old problems first, then I'm going to do some new problems. 20 minutes on the clock for old problems, and yeah, I'm just going to jump into it. So this is let's just say it's day 12 or 13. Whatever the video title is, that's the day. So I'm just going to jump into it. Binary tree Inorder Traversal. You know what? I'm feeling strong on this one, but I'm still divvying it up from... Oh, I saw a little bit of the solution. I'm going to block it and delete it. But, okay, so we have a binary tree node for a class. We have val, left, and right, and constructor for all three. Function Inorder Traversal is a root. We're passing in a tree node, which has left, right, and val, and we're returning an array. So given the root of a binary tree, so given node 1, return the in-order traversal of its node's values. So in-order traversal is a version of depth first search, which has 3 versions based on the order of the main node. So in order would be L and R. And so this is, I think, the recursive version of this is trivial, but iteratively might be difficult. So the recursive version looks like a function that we're going to pass an array into, and then we're going to recurse through the root node to push elements into this array. So create a temporary array here that we're going to return called nums, and then we're going to call helper, right, with our root node passing in nums, right? So we're going to have this function helper. It's going to take a node, which is going to be a tree node or null, and we're going to pass in nums, which is going to be an array of numbers, and we're actually not going to return anything at all because we're passing in nums by reference, right? And so how do we know that we can actually add a number onto the stack? I mean, add a number into this array, right? The minimum barrier required to even begin processing this node is that it has to exist, right? So we want to check if the node exists, right? This if block also serves as a way to end when we reach, null leaves of nodes. For example, one has a null here, but we just omit it from the graph image. So yes, actually, let me do something real quick. Okay, I'm back. Okay, we got gigantic cursor now, or thick cursor now. So they're omitting the left-hand side of this one here, but it's just because the left-hand subtree is null, right? So if node exists, right, then we want to process something, right? Otherwise, right, we don't want to do anything at all. We're not even going to return anything, right, because we don't want to add null elements onto the list. We can see this from the input that we have null here, and so we have node, left, right, node, right? And we can see that for null, for one, the left-hand subtree is null, right? But in the output, we actually omit the nulls, right? And so that's what we're going to do. So LNR looks like this. So what we would do is we would go left first, right? And so when we're going left first, just going to call helper again, but with node.left passing in nums, right? And the beautiful part is that tab being a little weird here, actually. Tab's a little strong. I actually didn't even start the timer. We're just going to say that I'm at 17. We're at helper, right? So L and R, right? So we're going to call left first, right? And left, we're going to go left, right? And then, so we can imagine if we pass in root, right, which is this root node here, we're going to do helper node.left, right? The one does exist, right? So we're going to go into this line 17, we're going to call helper node.left. Well, node.left is null. We're going to call helper again, push a call this function onto the stack, right? A good way to visualize recursive functions with a stack, right? So we had this original call with 1, now we're at the next call with null, right? And when we called it with null, we said we only do something if the node exists. Since it doesn't exist, we're not going to do anything, and we're going to come back to the end part of LNR. So we're going to do nums.push node.val. Then here we're going to do the final part of L and R, which is the R part, which we're going to pass in the right node, right? And so we're going to push 1 onto the stack, 1 on into the array. Then we're going to call node.right. Well, node.right of 1 is 2. While we go into 2, we're going to call this function onto the stack, right? Does 2 exist? 2 does exist, so we're going to go to line 17. We're going to call helper.node.left, right? So now we're going to be in 3. We're going to push a function call with 3 onto the stack. Well, does 3 exist? It does. We're going to go into line 17. We're going to call helper.node.left for 3, right? Now we're in 3's left subtree. 3's left subtree is null. Well, since the node doesn't exist, we're not going to do anything. We're going to pop that call. We're going to go back to 3, and we're going to push node.val, which is going to be 3. Then we're going to do helper node.right. We're still in 3. Right? We're going to push a function call of helper onto the stack, right? And it's going to be null, right? Because the right subtree of 3 is null. The node doesn't exist, so we don't do anything. We pop that null function of helper off the stack. We pop 3 off the stack because we just called helper, and we pop those 2 off. Now we're back at 2, right? And so when we last called helper with 2, we did helper node.left, which is line 17. Now we're going to do line 18, which is nums.push, and then helper node.right. We're going to push null onto the stack. It's going to be null, and then this should work. The time complexity and the space complexity of these recursive functions always confuse me. For this node, since we're just converting this binary tree node into an array of numbers, I'm gonna say the time complexity is gonna be linear time, because we have to visit every node in the tree. But the space that we use, I think, is also going to be linear space, because in terms of the functions that we push onto the stack, I think we're going to make like that many recursive calls as well, and our recursive calls are going to be tied to the time complexity, which was linear time. But this, I knew it was gonna, oh yeah, okay, so the space complexity is O of n. The worst case space required is O of n, and in the average case, it's O log of n, where n is the number of nodes. Okay, so now there's a follow-up, right? The recursive solution is trivial, okay? It's kind of harsh. Could you do it iteratively? So I think we can do this iteratively. It took me like 40 minutes to figure this out last time. So I'm gonna try and get this in less time. We have 12 minutes. I know it requires 2 double while loops, and there's gonna be an L and an R portion. We also tried to make an iterative version of a binary search, which was kind of convoluted. But for the iterative version of L and R, we're going to need for depth first search, we're going to need a stack, right? We could just use an array, right, and just only operate at the end of the array. So we're gonna say let, we're never gonna assign the stack, so we're just, we're never gonna reassign this variable, we're gonna be popping and pushing on the end. So we'll have a stack, and we're gonna have cur, right, which is gonna represent the current node that we're at, right? So while cur does not equal null, right, and, or actually, because these are actually, this wants to be an or. If it's and, this loop actually wouldn't run because the stack starts empty. So if, right, because cur wouldn't be null and the stack would have an element and would not have an element in it. So if cur is null or the stack isn't empty, which means we haven't finished visiting all our nodes, then we want to keep running this loop, right? And then I'm going to close this bottom window up here. I just realized you can barely see because my screen is so big. Oh man, that's so cringe. Oh man, that's bad. I'll do like this. And I'll push LeetCode to the left like this. That way it's easier to see all the fixins. Okay, so this is what we have so far. Okay, I have to make sure it can be seen. I'll put the timer back up. We have 10 minutes left. I'll put the timer down here, I guess. So you have 10 minutes, or I'll leave it up here. So we're gonna need another while loop, right? And what this while loop is gonna do is actually gonna enforce the L part of this L and R iteration, right? Right, because then when you do it recursively, the recursive calls make it certain, right? Since they work basically on a stack, right? We said the best way to visualize recursion was using a stack of function calls that you're recursing through. So the way to actually do this iteratively is to also use a stack, right? And so while cur, right, doesn't equal null, right, we're actually going to set up, right, that same rule that recursion enforces, right? So we never process the next line, right? The end part of our previous solution, right? The ln, the end part of the lnr, we never process it until we call helper.left. I mean helper with node.left first, right? So that is what this inner while loop is going to be enforcing, right? So while cur does not equal null, right, we're going to push the current node onto the stack, and then we're going to go cur equals cur.left. So we're saying, hey, I'm going to come back to this node, but I'm going to go left first, right? So we're going to go left, right, and we're going to run this again. So we want to go as far left as possible first. This is kind of exactly how recursion works. So this while loop kind of fakes this recursion enforcement rule from like kind of just the way that code order runs in. I think. And then actually maybe it makes more sense just do it like this. I'm so distracted today, but anyways, it should go like this, and now we can see the code better. While cur does not equal null, we're going to push the current node onto the stack and then go left, and we're going to keep doing that until we can't go left anymore. So once we exit this loop, we'll have gone as far left as we can, right? Once we've gone as far left as we can, right, well, what do we want to do? Well, once we've gone as far left as we can, we know that cur equals null, right? So we've reached pretty much the null node of the leftmost, I guess, leaf node, right? So there's nothing to do with cur as it is, so what we can do is set cur equal to stack.pop. And what that's going to give us is that node right before the left hand null. So if we imagine this for 1, right, cur equals root, which is 1, while cur doesn't equal null, 1 is not null, and the stack isn't empty, right? It doesn't matter because cur doesn't equal null, so we're just going to go in. So cur doesn't equal null because 1 is not null. We're going to push 1 onto the stack and do cur.left, right? Cur.left right now equals null. We go back to the top of this loop at 19. Does cur equal null? Well, it does equal null, right? Because we're now here, right, in this imaginary null node. Since we're here, if we pop, if we do cur equals stack.pop, well, what was the last thing that we pushed onto the stack? It was 1. So now we're back at 1, right? And so that is actually perfect. So what we'll do there is we're still gonna need nums, right? Because we're converting this binary tree into an array using Inorder Traversal. Or we want to return the Inorder Traversal of this node's values as an array. So we're still gonna need this nums array. I'm gonna do nums dot push no cur dot val. So I think that makes sense, right? And then from here, what we want to do is go right. And so what we would do here is we would say cur equals cur dot right. And since cur would equal, so we go from 1, we'd set now cur is equal to 2, right? We'd go back to the top of this array, right? Well, cur isn't null, right? Because it's equal to 2, right? But the stack is empty. And then while cur does not equal null, all right, well, cur is equal to 2, so we're not null still. We're going to push 2 onto the stack. The stack is no longer empty again. Stack is no longer empty again. And then we're going to do cur dot left, right? So now we're actually equal to 3, right? So then we're going to go back to the top of this, right? And cur does not equal null. Well, 3 doesn't equal null. And we push 3 onto the stack. So, oh no, I'm going too fast. So we're at 2. We push 2 onto the stack. Now cur equals cur dot left. So cur now equals 3. All right, we go back to the top of line 20. Cur equals 3. right? So it's not null. We're going to push 3 onto the stack. Now we're going to do cur equals cur.left. So now we're at this null point inside 3. Okay, since we're inside this null point inside 3, right, what's going to happen here? Well, null does equal null, so we're going to exit out of this loop. Right, we're going to pop the most recent number off the stack. It's going to be 3. We're going to push nums.curvi, which is going to be 3, and then do cur equals cur.right. So now we're going to try and go right. We're going to go to the top of the loop, and cur is actually going to be null. But the stack isn't empty, right, because 2 is still in the stack. And so since 2 is still in the stack, we're going to enter this loop again, right? And we're going to say while cur does not equal null, right? Well, cur actually does equal null since we're at cur.right, right? This node right here. So we're going to do cur equals stack.pop. So now we're going to go all the way back to 2, which is perfect. We're going to do nums.push cur.val, which is going to be 2, and then cur equals cur.right. And then we're going to go into that, right? And then cur actually is null, right? And the stack is empty, right? So this is going to fail. And cur actually is null, so this is also going to fail. So we exit, right? And then we can return nums. I'm feeling confident about this one. So let's see if it worked. Nice. So I think what's interesting about recursive problems is you only ever do one processing step, and it seems to be that's wherever n is. So the processing for depth first search at least seems to be, or for depth first searches seem to be done wherever n is. I don't think I've ever done a breadth first search yet, where you would visit the nodes according to height. But that's interesting. Another way to visualize this is that in the while loop we're doing L, right out here we're doing N, and then right here we're doing R. But I think what's also kind of cool is that, like I said earlier, all the processing mainly happens right here inside wherever N is. So that looks good. We'll pass that. And I think we only did one problem actually, because it was a main one and a follow-up. And we have about 2 minutes left. I'll do number of 1 bits just really fast, just because we can speed run it. I'm actually not going to read the problem for this, because I know we're just counting the number of bits that have 1 in it. So we're given a number, right? We have to count the number of bits, right, where it's set to 1. Also known as the Hamming weight. So to calculate the Hamming weight, we can assume that you know, the integers, at least maybe in JavaScript, are going to be 32 bits. I should Google that another time. But one way to start would just be to do 32 operations. So this would be constant time. And we could have a number ham, which is going to start at 0. We'll return ham. And we could do ham and, or do ham plus equal n, which is a number we have to count the number of ones in. And we'll mask it with 1. And basically what we're doing is, if we had the number 4 represented in binary, or 3 represented in binary, we're masking it with this, right? And we're saying, hey, does the 1 bit that we're masking this with, we're doing an and. So if they're both 1, we're going to get 1, right? And so n and 1, we're just going to do plus equal that, right? Then we're going to have to, what we can do differently is we can slide the bits in n down. So we can do something like n equals, and we'll bit shift it once to the right. I think this ends up being correct, but one of the things that's a problem, I think, is that we're mutating the function input, right? Which is a little bit weird. So I think a better way to do this, which I actually learned yesterday, is instead to have a mask, which will start at 1. And we'll do ham plus equal n and mask. And instead of sliding n, which is a parameter that they're passing into the function, we're just going to shift the mask instead, right? But we don't want to shift it right? If we take the same example we had earlier, 0011 and 0001, if we slide our mask down 1 bit, we're actually going to get 000, right? So what we want to do is slide it over 1, right? So we can get 001, 0, and then we'll mask it with ham, and then that should give us a good answer, or I guess a safer answer. Oh, so my input was 1011 and my output was 11. They expected 3. Mask equal mask bit shift right. Interesting. Interesting. I wonder why that is actually. So we're doing ham plus equal n and mask. N is what they passed in. Now we're shifting the mask 1 bit to the left. But if you bit shift 1011, I mean 1, then you should get 010.
Ooh.
So why is that performing that way? That is strange. Maybe there's something I'm misunderstanding here about how bit shifting right works. I'm misunderstanding something about how bit shifting right works. Since we already got it right the first time, and I was just trying to do it as a simpler way, this time I'm going to just read the solution as to how you would have shifted the mask. If n and mask does not equal 0, bits plus plus mask. So it looks like they're shifting it the same way I am. So this looks like they're shifting it the same way that I am, except they're using a shorthand. I've never used that shorthand before, but I'm not seeing why. Their mask also starts at 1. I call it ham, they call it bits. We're both doing 32 iterations. If n and mask that is strange. That is strange. That is actually strange. You know what? Let me see something. Actually, no. That is actually strange. I actually don't know why I'm shifting it the same way they're shifting it, but I'm not getting the same answer. That's a little strange. Interesting. That is interesting. I think it's because after reading that submission, apparently there's a difference between signed bit shift and unsigned bit shift. So they're taking an unsigned integer. Maybe the reason this is failing is because we're not using an unsigned bit shift. Right character expected. You know what? That is an interesting problem, but gotta keep it pushing. I'm still gonna tag this as pass, and I'm gonna go to, did those two. Let's try, 20 minutes on the clock. I'm gonna, 20 is kind of long. I'm gonna do 15. Let me make this bigger so it pops out more. So we have Excel sheet column number, function title to number. We have column title, which is a string, and number. So given a string column title that represents the column title as appears in an Excel sheet, return its corresponding column number. So A goes to 1, B goes to 2, C goes to 3, Z goes to 26. AA goes to 27, AB goes to 28. Title AB equals 2 times 8. So ZY, it looks like this is really just asking for us to convert a number in base 26, convert a string, which really represents a number, from base 26. I mean, the column title represents a number, but in base 26. So if we have 26 numbers in this symbol, in this set of symbols, right? We can tell it's a base problem because once you go to 27, we just restart with 2 of the same digits, right? 2 of this first symbol. So it's the same thing in And so how this works is if we have something like AA, that we know this translates to 27, right? Because of the same way that our number system works, which is 45. How do we know that 45 actually equals 45? Well, you break it down into the sum of the series of its constituent elements tied to the power for the base. What I mean by that is this would be 4 times 10 to the 1. And 10 to the 1 equals 10, right? Plus 5 times 10 to the 0, right? Which equals 40 plus 5. Same thing for A. A is the ones element of the symbol system, so it's 1 times 26 to the 1 plus A, which is 1, right, times 26 to the 0, right, which equals 1, which basically means 26 plus 1 equals 27. So we just have to convert this number, or calculate the value for this base 26 string. So base 26 string to number. How would you go about doing this? Well, we need some sort of implicit value for, A, B, C, and so on. And since, let's check if all the input is automatically uppercase. Okay, perfect. Column length is never greater than 7. So since it's all uppercase, what we could do is, since I think A starts at position 75 in the ASCII table, in the ASCII table, we need to shift all these values down to their actual values, right? So A should represent 1, Z should represent 26, right? So how do we go about doing that? I think what we could do is simply do, if A represents 75, you could do A minus 75, or the A dot, the, A, right, dot car code at 0, right, minus 75, and it should give us, or 74, it should give us 1, thus shifting them all down by 1. But I don't know if that's lowercase a or uppercase a. And so, you could test that if we had like a little environment or something, but I tried to leave the tabs during the video. So we're just gonna guess a little bit. So now we just need to sum the series. So we'll just say sum equals 0, and we'll iterate over let car of column title. Right, and what we want to do is do sum plus equal, right? And we're also going to need it's also a little bit easier if we iterate in reverse. So I'll say while I equals column title, right, dot length minus 1, I is greater than or equal to 0, I minus minus. And while we're iterating in reverse, we're going to get the last value in the array, in the string, right? And we're going to need to multiply it by its place. And it would just keep a value called power, right? And we're gonna do sum plus column title dot car code at I minus 74, right, to shift it down, right, times 26 to the power, right? And then we do power plus equals 1, and we should be able to return sum. There's a little bit of wishy-washiness in this just because I'm a little bit uncertain as to the ASCII values, and also I'm not feeling very confident about this iterating in reverse while I is greater than or equal to 0, I minus minus. So our iteration is going to start in reverse, which means we're going to access A first, right? Or yeah, we're going to access A first, and we'll just change this to AB, right? And the answer here should be 28. We're going to access B first. We're going to do sum plus equals column title dot car code at I, car code at I, right? If the length is 2, minus I is going to be length 2 minus 1, which is index 1, which is B. Right, you get the car code of that, we subtract 74 from it, right, to shift it down. Then we're going to do, hopefully we get 2, and we're going to do multiply it by 26 to the 0th power, should be 2 times 1, which equals 2. The power plus equal 1. We shall see. Car code, oh, I put car chode at, oops. So we're getting negative 24. That is strange. They expected 1. So how did this happen? Let's run this for A. Sum equals 0, power equals 0, I is less than column length minus 1. So the title is 1 character long, right? I is going to be set to 0. I'm going to say, well, I is greater than or equal to 0. So we actually are going to run this first iteration. We're going to do sum plus equal column title dot car code I, which is index 0, minus 74 times 26 to the 0th power, which should equal 1, but we're getting negative 24. I'm going to comment out this part just to see if I'm shifting down correctly. We should get 1, I think. but I'm getting -9. So maybe it's 74 plus 26, so maybe 74 is actually, 75 represents lowercase a. If we add 26 to it, we should get uppercase a, right? 75 plus 26 is 101, and we don't want to cancel out completely, so we'll do minus 100. I'm getting -35. That's so strange. $75, we got -9. Maybe it's not 76, maybe it's 66. Maybe it's at position 64. Maybe A starts at 65, and if we subtract 64, we should get 1. Okay, so A starts at 65. Capital A starts at 65, apparently. So that's cool. And then we'll add 26, right? Multiply by 26 to the power. This should still give us 1. So we got 1 times, let me PEMDAS this real quick. Oh wait, I don't think bracket is even, is caret even allowed as an exponent? Yeah, I think this is actually a bitwise operator. What am I doing? It would be double times basically for exponents. So that looks good. I think the number of operations here is times the time complexity is going to be linear time, where n is the number of characters in the string, with constant space, since none of the variables we use are going to scale with arbitrarily large input into the function. Key points about this problem is that it is the capital A ASCII value starts at 65. So that's probably important to remember. And yes, looks good. So Excel sheet column number, and then we have class TwoSum. Oof. I don't even remember how to do regular TwoSum. So we have a class TwoSum, we have a constructor, we have 3 minutes, we have add, which is a number, and find, which finds a value for a number, which takes value as a parameter and returns a Boolean. Okay. Also, how is number allowed as an identifier? Isn't number a data type or an interface type? Design a data structure that accepts a stream of integers. Stream of integers and checks if it has a pair of integers that sum up to a particular value. Implement the TwoSum class. TwoSum initialize the TwoSum object with an empty array initially. Okay, with an empty array initially. Okay. I guess you could just say R. Is that R equals this? It's gonna be wrong, but I just want to see if it's a okay, so we didn't. Okay, so you can just put R colon. Adds number to the data structure. Boolean find returns true if there exists any pair of numbers whose sum is equal to value. Otherwise, it returns false. Some add, find. So we add 1, 3, and 5, and we want to find if there are two numbers that add up to make any pair of numbers whose sum is equal to value. So are there any numbers that add up to 4? Yes. Any numbers that add up to 7? False. I think you could do this if we add numbers to an array. I think there's a reason they're giving us access to this add function. We do r.push. And in fact, you know what? Let's just say r.push. We don't actually have to return the indices, so we just do r.push number. We could also have a map. No, we could also have a set. So this dot set equals new set, and we're gonna say this dot set dot add number. And if we want to check if two numbers can sum up to a value, we could check. We could return if this dot set dot has value. So they're asking us to find basically the number 1. So you would say for anything add up. Wait, they're calling find with 5. Any numbers add up to 5. I tried to speed run it since there were 2 minutes left. Do any numbers add up to 5 if they're passing in 4? To 5. I think there's a linear time solution to this. Maybe not actually. This dot set dot has you can do this in n squared time if you just check every pair with every number. That's a bit slow. 3 numbers that add up to 5. I don't think I even know how to do regular 2-sum. So 2-sum data structure, a bit hard. Only 1/3 of people pass this one. Sign data structure that accepts a stream of integers and checks if it has a pair of integers that's similar to a particular value. Implement 2-sum class. You know, I'm going to put a struggle timer on at 5 minutes. Design a data structure accepts a stream of integers and checks if it has a pair of integers similar to a particular value. You could do this in n squared time. You would just have to do double for loop over the array and check if 2 values add up to equal value. That is very slow. Can you do this in linear time? If we've added all the numbers, possible numbers that could add up to 5. Yes. No. Yes, we could do it with a set, and I think this would be linear time, actually. It would be linear time, or maybe it wouldn't. The goal with the set is if we have the set, right, we'll be able to instantly know if a number exists in the set, right? So the goal would be every time we add a number to the array, we'll iterate through all the numbers that exist and add the sum of that number and the new number we're adding to the set. When we do find, we can just return if the value exists in the set. So we would do for let num, actually let's just do let I equals 0, I is less than r dot length, I plus plus, and then what we'll add into the set is actually the sum of number that you're giving us and the current number in the array. So I'm feeling pretty confident about this one. I don't know if it's, oh, I've done this one before. I don't, when was the last time I did it? I actually did it a year ago, almost a year ago today. No, almost a year and some change ago. So if I do toSum, add 0 into the array, and then I try to find if two numbers can sum up to 0, is 0 just an edge case? Two numbers can't sum up to 0, but find would technically make this true. 0 is an edge case. Basically, when we push, we just want to ignore 0. If number is not equal 0. Are there more cases like that? Are there more cases like that where it's impossible to sum up to a number? So we're adding 3 zeros, and then we want to find if 0 exists. Wait, that makes no sense. I thought we said false because 2 zeros. So why did this one fail and the other one not fail? If we have 2 adds, right, we're adding 2 zeros. Can we find, let me read the description. Returns true if there exists any pair of numbers. Any pair. So if we don't have a pair for a number, we shouldn't be able to say if it returns true. So we do want to add I think actually we could do this. What we could do it with a set is we want to know it exists and the number of occurrences. So we could change this to a map. We'll create a new map. We have 24 seconds. We'll add it to the map. We'll have to do set the sum of the number, right? But the occurrence would be 0. And the map could set the value for map.get number or 0 if it doesn't exist. Now this is very ghetto. We have const value which equals if the map has a value for number, will return map.get number, otherwise we'll return 0. And for the number, we will return we'll set the number equal to a value plus 1. So what's the goal, right? When we add numbers to the map that are being pushed into the array, we want to add them to the map with their number of occurrences. And when we want to check if two numbers can sum up to a value, we can just check if the number exists in the map. If the number exists in the array, right, we'll only add it to the map if the number occurrence is greater than or equal to 2 and IOC. So if we do map.get this dot array sub I, right, would get us the occurrences for that number, or 0 if it doesn't exist, and I is greater than or equal to 2, we want to say that this number does exist in the array, but with an occurrence of 1, because it's actually not a pair. This dot map. Oops. Map. I still have. Okay. Map. I'm not using set anymore. Set and get. IOD. Get value. Oh, I think we can also use map.has. If I name bat, you mean? Always forget. Without the actual IDE, a lot of these little changes get me. This not map IOC. Find name number awk. Oh brother, I'm so used to it lighting up and just telling me we have line 11 number awk. So we're adding a number if number, oh yeah, it doesn't matter if number equals 0 anymore. So you can remove that. At 1, 3, and 5, when we find 4, I never even started the 5-minute timer. At 1, 3, and 5, we check if we can find 4 in the map. Apparently 4 doesn't exist in the map. We don't need 2 occurrences of each. We need at least 1 occurrence of each to add it to the map. I'm not submit, I meant to click run. So solution works, but it still fails at the same case where this dot map has value, where the map does have the value, maybe it needs to check the number of occurrences. If value we're checking for equals 0, then return this dot get value 0 equals 2. Otherwise, you would return if the map has the value. Oh, not equal, or more than, greater than or equal to 2, but. Right, and so this one might be I think is a greater than equal to error, because we're adding 2. We say, can we find 0? Well, if value equals 0, it does. We're going to return this dot map dot get value. So it should be 2 with a number of I'm just guessing at this point. Usually you should I run the code in my head to figure out what's going on. but I'm just making changes and praying to the gods that it works. I think what this means is that I made a submission to this a year ago and it was working fine. So I wonder what I did there. So we have R and we have sorted. .push, this does add a number. So we push an array onto the data structure. We say this does sort equals false. When we want to find a number, we sort it, and then we use a two-pointer approach. This is not the two-pointer approach. This is a binary search. Dang, I was going crazy a year ago. Oh my God. I was really in my bag. That makes sense though. Maybe that's why they're... This wouldn't have been constant time anyway. I mean, this wouldn't have been linear time anyway, because every time you add a number, you have to do n. Every time you add a number, you could potentially do n operations. So it was still n squared anyway, except it was more... No, it wasn't even n squared. It's n by n. Every time you add a number, you have to add all the other numbers into the set just to make find constant time. Interesting. But I'm going to stop there. Thank you for tuning in if you did. Yeah, I'll be back again tomorrow for the grind.